Okay, can you see my screen?
It's up and running, yes.
Okay,
So,
great. Hello again. My name is Farhood from Concordia University, and I'm going to present our work pre-training language models for surface realization. So at first, I will introduce the problem. We will look at some of the previous work. And after that, I will introduce the model and show that how we gathered the data. And after that, our experimental result, and finally, the conclusion and future work. So natural language generation as a subfield of natural language processing is concerned about generating text in English or other human languages. And it has a wide range of applications such as report generation, visual assistant, and so on. Traditionally, energy pipelines are divided into three main steps: document planning to determine the content, micro-planning to determine the word, and surface realization to generate the surface form of the sentence in a simple word. It is responsible for word formatting and word ordering. Multilingual surface realization workshops for 3 years aimed to gather researcher focusing on surface realization. They held shared tasks to help the advancement of research in this area. Shared tasks were to generate the surface, the sentences, the surface form of sentences from an underlying representation. In this case, they used a universal dependency structure. They used a modified version of a universal dependency data set and asked the participant to reconstruct the sentences given their dependency parse tree. They considered two tracks, shallow and deep. In the shallow track, they removed the lemmatized form of tokens, and they shuffled the order of the tokens. In the deep track, they also, further than the shallow track, they also removed the functional words and asked the participant to ask the model to also guess those words. Here we can see an example of the dependency parse tree for the sentence. A large team of writers handled the script, where the morphological information of words are removed. For example, here, the lemmatized form of handled is handled. So some of the previous work that participate in the shared task, for example, a team from Vienna and Budapest University, they used an encoder-decoder model for inflection, and they used an interpreted regulatory grammar for the ordering tokens. Adapt Center, they used a rule-based module for inflection, and for the ordering part, they use an encoder-decoder module with the copy mechanism. And a team from University of Stuttgart, they combined the rule-based approach and encoder-decoder model for inflection, and they tackled the problem of ordering with the traveling salesperson problem. In terms of using external data, both Adapt Center and IMS, they used external data. They augment the data with external data. Adapt used more than 4 million samples, and IMS used around 200,000 samples. But what they did, they used word overlap and distribution of words, and also the branching factor of the trees to try to keep the distribution of the samples similar to the distribution of the manually labeled data in the universal dependency data set. And they also augmented the data. They trained their model on both data set at the same time. there were no adaptation or pre-training in their model. In our work, we use a single language model for both morphological and syntactic realization. And we also used around 500,000 synthetic samples to pre-train our model before training it. So for our model, we used BART. BART is a denoising autoencoder that trained to reconstruct the text. For surface realization, we feed the dependency parse tree as the input and train the model to generate the sentence. However, the language models are text-to-text problem, which means both the input and the output are presented in form of text. So we first need to represent our input, which is in form of graph, in form of text. For this purpose, we represent that the input graph as a linearized text. For example, here we can see the input graph, and on the right we have the feature of each node. For example, the node script, it's singular, its parent is token 5, which is handle, and dependency relation to the parent is object. And then at the end, we concatenated all the tokens and their feature into a single string to feed it to our model to generate the sentence. For the data set, the available data set that are available in the universal dependency data set, for English, we can see the statistic here. The largest data set, EWT, it has only 12,000 training samples, which is not a lot for training deep models. So we decided to use synthetic data for this purpose. We used stanza parser to parse the sentences and then use the script that provided by MSR Workshop to generate the data in the format of surface utilization shared task. We use 500,000 sentences from Wikitext, and again, using a stanza, we created the parse tree. We choose the sentences randomly, so the distribution of the sentences might be different from the distribution of data set that we have for fine-tuning. And we did not consider any filter to choose the data. Here we can see the results of our model with and without pre-training on synthetic data. On the top for the shallow track and on the bottom for the deep track. Rows with 0 means there were no pre-training on synthetic data, and other rows, that means we pre-trained with 100, 200, or 500,000 synthetic data. We can see that pre-training on synthetic data for both shallow and deep track, we have improvement, at least 3% improvement. And the improvement goes more than 20% for data sets where they have lower number of samples compared to EWT. And also the overall improvement, the delta in the deep track is much higher compared with the shallow track, which shows that our approach is effective. In comparison with other work, we achieved the state-of-the-art performance. For the deep track, we improved the state-of-the-art with a large margin. In case of the deep track, for the shallow track, our performance is below the state-of-the-art, and we need to do some improvement to be able to improve the performance of our model on the shallow track. Here we analyze the performance of the model on different epochs of training. Here is for training on EWT dataset. The blue line is with pre-training and the red line is without pre-training. As we can see, when we use pre-training after the first epoch, we almost achieve the peak of the performance. However, when we are using when we are not using pre-training approach, the improvement is almost toward the 8 epoch. So it means that pre-training help us to achieve the convergence much faster than without pre-training. In another experiment, in another analysis, we consider different size of manually labeled data. So we trained the model with 500,000 synthetic data, and then trained it with 1,000 from EWT dataset, 2,000 to all of the samples that we have in EWT dataset. So first of all, if we do not fine tune the model on EWT dataset, the performance is much lower, which means the distribution is far from EWT. But if we only train on 1,000 samples, then we can achieve higher performance than training on all the samples, but without pre-training. So that means pre-training helps us to use much lower samples for training. On the other hand, when we increase the number of samples, we can see that we have improvements. So that doesn't mean that using pre-training completely fix the issue of labeled data. If we have more labeled data, we will have better performance. Probably we don't have access to test it, but the result shows that. But again, if we pre-train and only use 1,000 samples, we can achieve a better result without compared to without pre-training. In terms of conclusion, so we propose a pre-training approach on synthetic data, which shows that it improves the overall performance of our model. It minimizes the requirement of large manually labeled data sets. We achieved the state-of-the-art performance on the deep track of surface realization shared task, but also we need some improvement on the shallow track. In terms of future work, we would like to test some ideas for the shallow track specifically, using copy mechanism, because in some of the cases we realized that there are some misspelling from the data. And also we can limit the vocabulary, the set of tokens to generate toward those that are appeared in the, and all the inflected form of them in the input. So the space that the model can generate, can choose the word from would be much lower, and it will improve the performance. Also, one thing that I'm currently working on is using multilingual model, a single multilingual, for example, embarked for all languages and training all at the same time. And another approach is cross-lingual inference, which means we train on one language and try to use the information, the knowledge on that language for another language, for example, training on English and testing on French. Okay, thank you, and I would be happy if you have any questions.